Okay, so we are going to continue with summation convention today. I hope you guys can hear me.
Yes, sir.
Okay, thank you.
Oh, yes.
Okay, so I was pretty much done with summation convention, but I would like to um, address one query that some of you had yesterday. That is whether the free index should appear in each of the terms. Okay, so no, suppose that I have a matrix C which is as follows. Um, so let us say this is no, it is formed by I into J, where I denotes the row and J denotes the column. So this implies that 1 1 is going to be 1, 1 2 is 2, 1 3 is 3, 2 1 is 2, 2 2 is 4, 2 3 is 6, 3 1 is 3, 3 2 is 6, and 3 3 is 9. Okay, so how do I write this in summation convention? So in summation convention, I will say that Cij is equal to Ij. All right. So here you see how many free indices are there? There are two free indices, both I and J, because they are appearing only once. So we have two free indices. In each of the terms. Now think of another example where you have the matrix C such that it is just formed by I. So in that case, 1 comma 1, so I means ith row. Okay, so the entry is the row itself, the row number. So first row, everything is then 1, 1, 1. Second row, everything is 2, 2, 2. And third row, everything is 3, 3, 3. Okay? And if I want to write this now in summation convention, I will say that Cij is equal to I, isn't it? So this is also a valid representation for the above matrix identity. Now you see that again I and J both are free indices. But J is not appearing on the right hand side. Okay, so basically the free indices did not appear in each of the terms. And this is perfectly valid expression. Also, you see, wherever you have three indices, for example, you have this I and this I. This I denotes the same index, isn't it? So if you want to change this I, you have to change it everywhere. So you can make it C Kj equal to K. So this is fine. But if you change it only at one location, let us say you say Ckj is equal to I, then this becomes wrong. So that's what we mean that if you have to change free index, you change it in all the terms. not that you just change in one of the terms and leave it elsewhere. Okay, so I hope it clarifies about the free index. I think Niranjana had this question yesterday, and also Pulkit perhaps.
Yes, sir. Sir, one more question. Like any physical system, or like is it only a mathematical concept about this? Like any free index may not appear in all the terms. Means is it true for any system also, like any tensor, stress tensor, or anything else?
Yeah, I mean, it is not just mathematical, it can be even physical. Let us say you have a matrix whose all the terms are same. Then what will be the expression? Cij is equal to some constant, isn't it? Let's say some
Yes.
C naught. And you can
Okay.
have such matrix appearing in physical system. So you can
Yes.
see that I and J are free indices, but it is not appearing on the right hand side.
Right, sir.
Yeah. Okay. Is there any query from the last lecture? If not, then I will proceed. Please ask me. By the way, whatever we are doing now, I am. You can also read them from volume 1 of Ave Ratne. Okay, and this is in chapter 1. Okay, so looks like you don't have any query, so I am going to proceed. I am just going to do some examples so that we get more familiar with summation convention. Okay. So this example is also in the book, by the way. So it says, think of this equation, y equal to ax plus bz. So the curly braces are to denote vectors, and the big bracket, they are to denote matrices. Okay? This is the convention that the book follows. So this is a matrix vector equation, right? And suppose I want to write this equation in index notation. Then how will I write it? So yi, the ith entry of y, what will that be equal to? To get the ith entry, I have to take the ith row of A and multiply with x. So ith row means A will have first index I, because first index is for row. And the second index then has to be summed because it is multiplied with x. So you can say aijxj. Okay. Likewise, you come to the second one, it becomes BIMZM. So you see that these two, it's a dummy index. So M could be anything. But the I or this I or this I, they are free index. And if you want to change it, you must change it. You must change them all together. It should not be that you are changing in only one of the terms and not in other terms. Okay? Either you don't change it or you are changing, then change it everywhere. And also see that in this example, the free index is appearing in each of the terms. Okay, let's do another example. So another one, it's a very nice example. It says think of two matrices, S and W. So S is symmetric and W is anti-symmetric. Okay. So if it is symmetric, how do I denote that in indicial notation? In index notation or in summation convention, how do I denote that the matrix is symmetric? So I will say that the ij component is equal to ji, isn't it? So Sij is equal to Sji. And for anti-symmetric, it would be Wij is equal to is equal to minus of Wji, isn't it? Okay. Now, what we have to prove is that Sij into Wij is equal to 0. So prove. For S symmetric and W anti-symmetric. Can we prove it? Just think of whether we can prove it or not. So, you know what we can do, Sij, Wij, we can say this is equal to minus of Sij into Wji, isn't it? From the antisymmetric nature, Wij is equal to minus of Wji. But also Sij is equal to Sji. So this becomes equal to minus of Sji into Wji. Now compare first and last. What do you think? Are they same or they are different? So I and
Same,
j
sir.
both are dummy indices here. So if you change I to j here and j to I, so change I to j and j to I, then it becomes Sji Wji. But here also you have the same thing but with a minus sign. So when is that possible? A number equal to negative of it, that's possible only if it is equal to 0. Right? So this is what we had to prove. So quite simple, isn't it? Okay. Now another one, let us do. Think of this example. So we have a matrix T which is multiplied with a vector U. Okay. So when you multiply a matrix with a vector, what you get is a vector, right? So the product is now a vector. And suppose I dot this with the same vector U. Okay. So can I write this in indicial notation? How to write this in indicial notation? So suppose that this is vector B. All right. Then in that case, what is Bi? So ith row of B should be equal to take the ith row of T and multiply with U. So this is T I J U J, isn't it? And then I have to do B dot U. And then it is B dot U, which is BIUI. So when you put it here, then that expression becomes TIJ UJ UI. Okay, so that is the indicial notation for that matrix vector expression. Okay. Well, this is not it. We have to prove that if we replace T by its symmetric part, so if we replace T by its symmetric part in the above expression, the result is unaffected. Okay. So how to prove that? So basically, suppose that symmetric part of T I denote by Ts. So Ts is the symmetric part. Okay, I'm having some problem with my pens. Symmetric part. So with Ts, when you work out that above expression, you will get Ts Ij Uj Ui. And we have to show that this is equal to the original expression Tij Uj Ui. Okay. So can we prove this? Anybody knows how to prove it?
So replace T with T plus T transpose divided by 2.
Replace T with T plus T transpose divided by 2.
The
So that is
symmetric
like
part. The symmetric part. Ts with.
And then
T of ij plus Tji divided by 2, and Tji is equal to Tij.
well, first of all, you can't replace T by its symmetric part because T and T symmetric are not the same. But yes, you can replace Ts by T plus T transpose by 2. So I guess what you mean is take the left hand side and write Tsij as Tij plus Tji divided by 2 into Uj Ui. Isn't it? This is what you mean.
Yes, sir. Yes.
Yes. And then work it out then. So this is then half of Tij Uj Ui plus Tji of Uj Ui. Okay. Now you see that this expression is there on the right hand side. But what do we do with the second expression? So in the second expression, when you interchange I and j, because they are dummy indices, no? So you can interchange I and j. So this becomes Tij Ui Uj. And now since they are all scalars, you can shuffle them. and this becomes Tij Uj Ui, because A into B into C is same as A into C into B. And now you see that this is same as here. And then it finally becomes Tij Uj Ui, right? And this is what you had to prove. Okay, so it was quite simple. And this also means that if you take the anti-symmetric part, so which I denote by TA, so TAIJ UJ UI, so this is anti-symmetric. And when you work this out, you will see that it is equal to 0. Maybe you should try to prove it later on, okay? All right, let's see some other example. Yeah, next, another nice example is that they want to evaluate this expression. Evaluate delta Ij, delta Ik, delta Jk. Okay, so you can see all the indices are appearing twice, so they are all dummy indices. So how do we work this out? So we know what is the job of Dirac delta function. So think of, for example, this repeating index. So Kronecker delta simply replaces the repeating index with its other index, that is j here. So this becomes delta Ij into delta Ij, isn't it? And then one more time, you have this repeating index j. So that repeating index is going to be replaced with I, and this becomes delta II. Okay. So what is this equal to? So if your I goes from 1 to 3, then it becomes equal to 3. If I goes from 1 to 3. Okay, very simple example. I'm just trying to see some more nice examples. Okay, there is another one. So it is epsilon ijk into epsilon kij. So what is this going to become? So here we have to apply that epsilon delta relationship. So if you recall from yesterday, it was epsilon ijk into epsilon imn. So that is equal to, see, it is very easy to remember. So first you take the pairs. So you know that there are two things here, no? On the right hand side, you have 2 Dirac delta minus 2 Dirac deltas. Then we have to fill the subindex or subscript. Now in the first one, you take these combinations Jm and Kn, second and third. So it is Jm Kn. In the second one, you take the other pair. So that's Jn and Km. So this Jn and Km. Okay. So it's quite easy to remember. And now I want to apply this formula here. So to apply this formula, you see that the first index has to be the same. epsilon ijk, epsilon imn. So the first index is the same, right? So I want to do that here also. The first index here is I, so we have to make the first index here also I. So we can flip the index, right? Ki, we flip it to ik. And if we do that, we have to apply a minus sign, isn't it? So this becomes equal to minus epsilon ijk into epsilon ikj. Correct? Now you apply this relationship. So this is then equal to minus Dirac delta jk into Dirac delta kj minus Dirac delta jj into Dirac delta kk, isn't it? And let's now try to work this out. So here again you see that the index is repeating. So Kronecker delta removes that repeating index and replaces it with the other index. So this becomes minus delta jj, correct? Minus delta jj into delta kk. Okay? So what is this then? So this is delta jj is 3, right? Minus 3 into 3. So this is 6 finally. Okay? If you're not able to follow, please let me know. Okay, let's do another one. I'll do an example which is not there in this book. So, yeah, so all of you know about this cross product, isn't it? So A cross B. Take its magnitude and then square. What does this become? So you must be knowing that this is equal to magnitude of A into magnitude of B into sine theta, and then I take its square, isn't it? So this then becomes magnitude of A square into magnitude of B square into sine square theta, correct? And sine square theta is same as 1 minus cos square theta. So this is equal to then magnitude of A whole square into magnitude of B whole square minus magnitude of A whole square into magnitude of B whole square into cos square theta. Right? Are you with me? Okay. Now let us try to write this in indicial notation. So magnitude of A square, what is that equal to? Can someone tell me what is magnitude of A square in index notation?
AI square.
AI square. Well, you should never write AI square, because when you write AI square, what you see is that I is not repeating twice. So it is misleading. Don't write AI square. You can write AI into AI, but don't write AI square. Okay?
Okay.
So you can write AI into AI. Similarly, for magnitude of B square, what should you write? Someone else, can you tell me what should I write?
BI into BI.
BI into BI. But you see, I should also never write this because I is appearing 4 times now.
J into VJ.
BJ into BJ.
BJ into BJ, exactly. So I could write this as AI into AI into BJ into BJ minus. Now, what is this thing now? Magnitude of A square, magnitude of B square into cos square theta. Do you see that it is also equal to A dot B magnitude square? What is A dot B? That's magnitude of A into magnitude of B into cos theta, right? And then you take the square. Is that okay?
Yes, sir.
What do you think? Okay, very good. So this then becomes AI into AI into BJ into BJ minus, what is A dot B in index notation? So that's AI
BI.
BI. And I want it's a square. So I should write like this. What do you think, Adil? Is that okay? Adil is there? Can someone see if Adil is present? Because my screen is full. I can't see. Anyway, we should not write this also, just like we can't write
M is
AI
there,
square.
but
Don't write this. Can I write this as AI BI into AI BI? No, just as earlier. So what we can do is, this is AI AI BJ BJ minus AI BI into AJ BJ. Correct? So that's the proper index notation.
Sir,
For
can you
A
please,
cross magnitude square. Yes? Tell me.
sir, can you please repeat why we can't write AI square?
Yeah, I mean, see, when you write AI square, how do you know that I is being summed here?
Because
Because the
like
convention is, if an index is appearing twice, then you sum it. But as per this expression, I is appearing only once,
oh, I see.
so we don't know that it is being summed. Of course, if you are if you really know that, okay, square means it is AI into AI, and then it is being summed, then it is fine. But you know, when you work with index notation, you will have an expression which can run into 2 lines, 3 lines, 4 lines. And there it will be very difficult to track. If you just write AI squared, you might just mess up. So never do that. Okay?
Yes.
Anyway, we got it in this way. Let us try to obtain it in another way. So I have the same thing here. A cross B magnitude square. So now let us try to use the formula for cross product. What is A cross B? That is epsilon ijk aj bk ei. Isn't it? Recall from yesterday. So that is A cross B. And what we want is A cross B magnitude square. So this is same as vector A cross B dotted with the same vector. Isn't it? So I will then write it as epsilon ijk aj bk ei dot with. Now you should not repeat ijk again because you see ijk have already appeared twice. Use something else. For example, epsilon m and p a n b p e m. Correct? So I hope you are with me. Okay. So now you see these are all scalars. So these are scalars. And only EI and EM are vectors, and you have to take its dot product. So what is EI dot EM? What is this going to be equal to? So they are unit vectors perpendicular to each other, E1, E2, E3. So EI dot EM, it is going to be equal to 1 when I is equal to M. And otherwise it is 0, right? So we can write this as Kronecker delta IM. So finally, then this becomes epsilon ijk, epsilon m and p, aj bk, an bp, into Kronecker delta im. Is that okay? Now you see, think of, for example, this repeating index m, and you have Kronecker delta, so it is going to replace that repeating index with I. And this becomes then epsilon ijk into epsilon I and P into AJ, BK, AN, BP, right? Okay, now you can use that relationship, epsilon delta relationship, isn't it? So this becomes delta JN delta KP minus delta JP delta KN into AJ, BK, AN, BP. Okay, now let's try to work this out. So from the first term here, when you multiply, what is going to happen? So J is repeating twice and J gets replaced with N. Likewise, K is repeating twice, so K gets replaced with P. So the first multiplication will give me AN BP into AN BP minus the second one you see delta JP. So J gets replaced with P and delta KN. So K gets replaced with N. So now we have AP, BN, AN, and BP. Okay, so what is this now? So we are almost there. So you can write AN, AN, BP, BP minus AP, BP, BN, AN. And you see, isn't this what you have here? See, here also you have the same thing. But we just worked out in a different way. Right? If you want to further go back, you can see that AN is magnitude of AN, magnitude of vector A square. BP is magnitude of vector B square minus AP is A dot B, and BN is also A dot B. Okay, so this is what you had also earlier. Okay, so have you now mastered summation convention? Can you work out any problem now? What do you think? If there is any confusion, please ask me.
Sir,
Yeah,
sir, whenever like two terms are in a product and both two terms are same, like A cross B dot A cross B.
yes,
So always we have to use other indices for the second term.
yes, correct, correct. Because the summation convention says no index can appear more than twice. So therefore, for the second one, you have to use different index, like over here. Okay.
Yes, sir.
Anybody else has any question, or anyone would like to add something here? Because some of you perhaps know about this. So do you want to add something? SP Singh or Adil, do you guys want to add something? Okay, all right. So if there is nothing, then we finish summation convention and we will go to our next topic. And of course, when you go on internet, you will find several examples. Try to work them out as much as possible, and you will master it. And this is really, really useful for a student who is trying to do research in solid mechanics or also fluid mechanics. For them, it is very, very important. Okay, so the next topic is vectors and tensors. So we want to learn about vectors and tensors. So let's start with vectors. And this is, by the way, in chapter 2. Okay, chapter 2 of Abhay Ratne. Volume 1. And it has got many more things which are all very good. So you can read the entire chapter 2, but I won't be doing all of them. Okay? And at the same time, I will also be doing some extra things. Okay, so vectors and tensors. So what is a vector? Very basic question, isn't it? What is a vector? So you have learned, I think the first time you must have learned about this was perhaps class 9. So there you learned that a vector has got a magnitude and direction. So a scalar, for example, has got just magnitude. It has no direction, but vector has got this extra information of direction. Okay. So the length of the arrow, that is the magnitude, and orientation of the arrow is the direction. Let us say the points are A and B. Then several times you write this as AB with a bar above. All right. So that's the basic definition, of course. But now you are going to learn more things. Can anyone add something to this definition? Anybody? So of course, a vector has magnitude and direction. Does a vector have any other property?
Yes, sir. It should follow the laws of vector addition.
It should follow the laws of vector addition. See, when you are, well, when you say vector addition, then it is containing this word vector itself. And we are not yet clear about vector. So
Okay.
maybe try to say something else.
Sir, it is a physical quantity.
Yes. Well, need not be. It need not be a physical quantity. Because vectors can be in any dimension. It need not be in just three-dimensional space.
So vector, its value, it doesn't change with the change in coordinate system.
Okay, is that
It is a
Adil?
physical quantity. It is a physical quantity like velocity, or it always remains same. It changes with the coordinate system.
So what's your name?
Its value. So it's Vinayak.
Vinayak, okay. Okay, very good. So yeah, that's a very good point. That a vector is independent of the coordinate system. So where did you learn this? Vinayak.
Yes, sir. I read it in the book.
Okay. So what does this mean, by the way, that a vector is independent of the coordinate system? So, think of a coordinate system, for example. You have here E1, E2, and E3. So that's a coordinate system with origin at O. And then there's a vector V here. Now think of another coordinate system. Which could be E1 hat, E2 hat, and E3 hat. So it's a hat coordinate system. Or you can think of another one, tilde coordinate system. E1 tilde, E2 tilde, E3 tilde. So, this is like, for example, you are in a room and there's a vector in the room. And then you can think of several coordinate systems in the room, having origins at different corners of the room. One coordinate system having origin at one of the corners, another coordinate system having origin at another corner with a different basis vectors. And from each of the coordinate systems, you are watching the vector, that vector V, this vector V here. See, as you change the coordinate system, but the vector V is still suspended in the room at the same location. Nothing happens to the vector when you change the coordinate system. So that's what we mean to say that a vector is independent of the coordinate system. A vector itself is independent of the coordinate system. But then there are something which depends on the coordinate system. So what depends on the coordinate system is the component of the vector, isn't it? So in this coordinate system, the first coordinate system here, the component Vi will be equal to V dot EI. In this coordinate system, the component is going to be equal to Vi is equal to V dot EI hat. And here, Vi is equal to V dot EI tilde. So the components of a vector will of course change from coordinate system to other coordinate system. Because why it is so? Because component is always related to a direction. And when you change the coordinate system, the basis vector of the coordinate system changes. And therefore the component will also change. Let me draw another nice example. So you have a more specific example. So you have this E1, E2, and E3. And think of a red coordinate system having the same origin, which is E1 tilde, then E2 tilde, and E3 tilde. Okay, which is same as E3. And suppose this angle is 45 degrees. And think of a vector V, which is actually, let us say, 5 times E1 tilde. So that's the vector V. Now, how will this vector look like in the black coordinate system? So in the black coordinate system, you then have to find out its component related to each of the basis vectors of the coordinate system. So in the black coordinate system, you have V. So I will write it like this. V in black coordinate system. So the coordinate system is going to be written below: E1, E2, E3. And then write down the 3 components. So that is V dot E1, V dot E2, and V dot E3. So what does this become here? So you will see that this is 5 by root 2. This is also 5 by root 2. And this is 0. But when we again try to express this vector, let's say in the red coordinate system, it's the same vector, but expressing now in a different coordinate system: E1 tilde, E2 tilde, and E3 tilde. So this is now vector V dot E1 tilde, vector V dot E2 tilde, and vector V dot E3 tilde. Okay? And now when you work it out, you get 5, 0, 0. So what you see is that these two are different. So they depend on the coordinate system. And they are also called representation of a vector. Okay? So what we found out is that a vector itself is independent of the coordinate system, but its representation, which is also drawn by its column form, or we'll say column form. So in the column, you have to write 3 entries, isn't it? So that's a representation. So that changes from coordinate system to coordinate system. Changes from one coordinate system to other. Okay, so I hope this point is very, very clear to you. So vector, of course, has got a magnitude and direction, but it is also independent of the coordinate system. But its column form, that changes from one coordinate system to the other coordinate system. Any query till now?
Sir, anything is there which depends on the coordinate system?
Please say again.
You said that vector is independent of the coordinate system.
Yes.
Is there anything which depends, like any physical quantity that will always be independent of coordinate system? So, like, is there anything which depends on the coordinate system as well?
Okay. Yeah, I mean, that's a very good question. Usually the physical quantities are independent of the coordinate system. But of course, if you say the component of a vector, if you are trying to measure component of a vector, then of course it will depend on the coordinate system. Right? So if you say the component itself to be the physical quantity, then it is depending on the coordinate system.
So the
Yeah.
column form is giving us the components of the vector along those particular directions only.
Exactly. Yes. Yes. And that's why it is dependent on the coordinate system.
So, like, why we specifically talked about this point for vectors? Like, even scalar or a tensor means, will this case will be the same in those for scalars and tensors also?
Yeah, but why we say it? Because students always confuse. So you have to always remember that there is a difference between a vector and its column form. A vector and the column form, they are not the same. A column form is just the representation of a vector. It is just a representation. So you should remember that a vector and its column form, they are different.
Right, sir.
Yeah. Well, people really confuse themselves.
So
Yes.
by vector we just mean that there's a physical quantity, and column form is used to represent that physical quantity.
Yeah, you can say that, but at the same time, as I told you, a vector need not be always a physical quantity. It can also be an abstract mathematical quantity. For example, a vector in 6-dimensional space or 100th-dimensional space. It's not a physical quantity, but it's a mathematical abstract quantity. Okay? All right, and then, if you want to use summation convention here, you can say that a vector V is equal to V dot EI. And here automatically a summation over I is implied. And this is same as the vector V dot EI hat into EI hat. Okay? Which is also same as the vector V dot EI tilde into EI tilde. All right? Okay, so this is about vector. Now there are several operations involved with vectors. So operations with vectors. So see, we are going very slowly and basic things, but there is always something new. So don't lose your focus. So of course, the number one is dot product, which you all know. And this is also independent of coordinate system. It is independent of coordinate system. And that's why it is also said that it's a tensor operation. Well, I haven't yet talked about tensor, so let's not talk about that. So when you have two vectors A and B, the dot product means I have to write like this, A dot B. Okay, and in index notation, this is AIBI, correct? But what is AI, A1, A2, A3? They are the components of the vector A in some coordinate system, isn't it? So let me be more careful now. So you can't just write AIBI. So A dot B means you represent this vector A in some coordinate system, let us say E1, E2, E3, and also represent the vector V in the same coordinate system. See, both of them have to be represented in the same coordinate system. It should not be that one of them you are representing in E1, E2, E3, and the other one is E1 tilde, E2 tilde, E3 tilde. Then transpose the first one and then multiply. Okay, so after transposing, this becomes 3 cross 1. So this becomes 1 cross 3 after transposing. So this is 1 cross 3 after transposing, and this is 3 cross 1. And when you multiply, you get 1 into 1. And you can see when you multiply, you get AIBI. Okay? So if somebody directly tells you that A dot B is AIBI, then you might think that it is, so it seems like it depends on the coordinate system. So when I say A dot B is equal to AIBI, so it looks like it is dependent on coordinate system, isn't it? Why? Because the formula involves components of the vectors A1, A2, A3, B1, B2, B3, which are itself dependent on the coordinate system. So if you choose different coordinate system, you might get AI hat, BI hat, or you get AI tilde, BI tilde. So from this, it looks like the three need not be the same. But it turns out when you work out this multiplication and sum it, then the all three give you the same result. So it is therefore independent of the coordinate system. So I hope you can see what I'm saying. So basically, whenever you want to do A dot B, you have to represent both A and B in the same coordinate system and then work out the dot product. Now you see it is getting a bit complex because earlier you never thought that you can represent a vector in different coordinate system. You were simply writing AIBI. But now you see that both A and B have to be represented in the same coordinate system. Of course, the final formula is same AIBI, but you have to remember that both are in the same coordinate system. And the other way to see that it is independent of the coordinate system is the physical formula, that is magnitude of A into magnitude of B into cos theta. So you have a vector A and another vector B, and that's the angle theta. So as you change the coordinate system, the magnitude of the vector does not change, and likewise the angle between them also does not change, and therefore this quantity does not change, and therefore we say that A dot B is independent of the coordinate system. So from here it is very easy to see that yes, it is independent of the coordinate system. But when you look at AIBI, then you get a bit confused. But it finally turns out to be independent of the coordinate system. Okay? So that was dot product. The second one is cross product. And dot product, by the way, is also called scalar product because it gives you a scalar, right? A and B are vectors, but after dotting, it becomes a scalar. Cross product is also called vector product. Okay, now A cross B. Do you have any query?
Yeah, excuse me, sir.
Yes.
So if vectors are not in the same coordinate system, then can't we do A dot B?
Please second, if they are not in the same coordinate system,
Then we can operate A dot B or we cannot operate A dot B.
okay, first of all, vectors are never associated with a coordinate system. A vector is independent of the coordinate system. Its column form is associated with a coordinate system. Okay? I hope you
Okay, sir.
understand that.
Yes, yeah.
Now, when you want to do the dot product, see, dot product you can always do. But when applying the formula, you have to be careful. When you want to apply the formula AI into BI, then the AIs and BIs must be the component of the two vectors in the same coordinate system. This should not be the components in two different coordinate systems.
Okay.
Only then you can apply the formula AI BI.
Okay, sir.
Okay?
Yeah.
What's your name?
Rajneesh.
Rajneesh, okay. All right. So A cross B. So you can also think of it graphically. You have a vector A and then the vector B, and here's an angle theta. And think of this parallelogram. And this parallelogram will have some normal n, isn't it? So if I shade this parallelogram, then A cross B is nothing but the area vector of the parallelogram. It's called the area vector of the parallelogram. So which is area times the normal. And the area of the parallelogram is magnitude of A cross B. And the normal is pointing in the direction of A cross B. Okay? And how do you obtain the direction? You have to use the right hand thumb rule. Take your right hand, move your fingers from A to B, and the direction in which your thumb points, that's the direction of the A cross B. Okay? So you can use here right hand thumb rule. All right. So this is the geometric definition. But again, if you want to work it out in a coordinate system, then you have to write both A and B in the same coordinate system. Same. You write the column form, but both should be in the same coordinate system. And then you can work out the formula. Okay? You should never mix up the coordinate system. All right. There's another very nice property of cross product. And I think this is something not every one of you have seen it. So we know this A cross B from the indicial notation, we know that this is equal to epsilon ijk ai bj, sorry, aj bk. We could have also done the other one, but let's stick to the one that we learned here. So aj bk ei. So this is the formula for A cross B. What I want to say you is that you can also realize this A cross B as a matrix times the column of B. Okay, let us see how we can realize this. And for that, I'm going to use this formula here. So what I said, it is a matrix multiplied by the column of B. Look at this formula, epsilon I j k a j b k e I. So suppose A cross B is C. So C is equal to A cross B, which is equal to this. So this implies that Ci is simply epsilon ijk into aj into bk, correct? Or this is also equal to epsilon ijk into aj into bk. Now this thing inside the bracket, let us say this is some big A ik into bk. I'm just defining it as big A ik. All right. So Ci is big A ik into bk. And from this formula, you know that this means you have the column of C equal to the matrix of A multiplied with the column of B, isn't it? So can we identify the components of this big A? So let's try to identify this component of big A. And we know that aik is epsilon ijk aj. So what will be A11, for example? Put I equal to 1 and k equal to 1. What will you get? Can you see what am I going to get? Yes?
Diagonal matrix?
Diagonal matrix. No, you just tell me what is A11. I equal to
0,
1, k. Sorry?
0?
0, yes. Because epsilon, two of the index are same, so you get 0.
Yes.
Likewise, A22 is also 0 and A33 is also 0. Now come to A12. So A12, this is epsilon 1j2 aj. Now epsilon 1j2 will be non-zero only when j is equal to 3. But epsilon 132 is minus 1. So what you have here is minus A3, isn't it? Likewise, you will see that this term here will be A2 and this term here will be minus A1. And this will be A1, this will be minus A2, and this will be A3. So this matrix will be such that it's a skew symmetric matrix. A skew symmetric matrix formed by components of A. All right. So what we have just found out is that the cross product, when I said that C is equal to A cross B, then this is actually also realizable as a matrix A multiplied by the column of B. And this matrix A is such that Aij, or well, I had Aik, so let us just use that. It will be easier. Aik is equal to epsilon ijk Aj. Okay. So basically, you can also realize cross product as matrix vector multiplication. But the matrix is now of this form. So I think some of you must have seen this. Any question till now?
So how did you partition the original term? Like,
Hello, sir.
Yeah, say again.
Sir, please extend the session, sir. Actually, last day, sir, it automatically.
Okay.
Hello.
I mean, we have 10 minutes of time. I don't want to extend it. I will just end it before 16:30.
Okay, sir.
Yeah. Unless you want me to extend.
Sir, is this we have written aik is equal to epsilon of ijk into aij? Is this a property
Yes.
of this epsilon ijk that the j index vanishes?
No, J index is not vanishing. You are summing over J here, no?
Okay.
Sum over J, it's a dummy index, so therefore it will not appear on the left hand side. On the left hand side, A, I, J, they are all free indices.
Okay, sir. Okay, sir.
Any more question?
sir, in the original term, you wrote like Ci is equal to epsilon ijk aj bk. So how do we come to know that we can partition any expression, and that partition will be matrices like that means?
Okay, yeah, that's a very good question. So look at this formula. So this is C, and from here we deduce that Ci is this. Okay, and then again I wrote it like this.
Yes, sir.
Now you can see that the thing inside the bracket has got two free index, I and k.
Yes, sir.
You can always think of a matrix whose components are formed by this formula, right? Because it has got two free index, you can always associate a matrix to it,
Okay.
right? It has got two free index, so you can always associate a matrix. So that's what I did here. I said, let us say it is AIK, and then A becomes a matrix, right?
Right, sir. Okay.
Okay. Any more question?
Sir, one small query.
Yeah.
Sir, in the starting of the class, one example you gave, y is equal to ax plus bz.
Yeah. The first
Can we
example.
write? Yes, sir. So can we write bz as bij zj?
Let me just go there. BZ BIK
bij
ZK.
zj.
Of course, we can do that because you see, M is a dummy index. You can replace it with anything. other
Can
than I of k. So yes, you can write it as BIKZK.
no, sir, BIJZJ. I am talking about J, which is the which
Oh
comes
yes,
in the
yes, you can also do it as BIJZJ. There's no
oh,
problem because it's not like it's now repeating 4 times. You have to look at every term. So in each of the terms, it should be not more than twice. So
okay.
here on the right hand side, you have 2 terms. So while counting, don't count each of them and then sum it. You have to only look at individual terms and it should not be more than twice.
Okay. So, sir, like suppose I write the same thing instead of summation convention, I put the summation sign and I use
Yes.
J and M. J for the Aij Xj and M for Bim Zm.
Okay.
So, then how I will come to know whether I have to keep J constant and then keep M as 1, 2, 3, or I have to do J1 M1 and then J2 M2 means which is a better way? Whether should we use BIJZJ or BIMZM?
Well, both are same. What you are saying is if I explicitly use the summation symbol,
Yes,
right?
sir.
So you are saying if I say it like this, Aij Xj plus BIMZM.
Yes, sir.
So, so whether you do this or you say summation over J Aij Xj plus BIJXJ,
Okay.
they are both the same thing. Maybe are you saying that when you write it in a program, then how is it going to be done? So in a program, for example, you will have a single loop for J
Okay.
and this will work out. For this one, if you want to associate individual loops for each of the index, dummy
Okay.
index, then you will have to have 2 loops. One loop over J, and that is just going to compute your first term.
Right.
And second loop over M, which will compute your second term, and then you have to sum them together. So here you will require 2 loops. But here, just one loop will do it.
Okay. But in the first term, the loops will be like simultaneous loops, not one inside the other. Means two
Yeah,
different loops,
it's not a nested loop, that is true. They are different loops, not nested loops.
not nested loops. Right.
Yes, of course, it is not nested. Yeah. See, nested would mean that it would be like this. If you have something like this, Aijxj into BIMZM,
So the session will end.
then you see it's actually a triple summation, no? It's a triple summation because I, J, M all are repeating. So you have a loop within another loop because it's a triple summation.
Understood, sir.
But yeah. Okay, so there is just 1 minute left. So I think we can close the discussion today.